All right, in this explainer, we're going under the hood of the chips that power, well, pretty much your entire world. We're going to explore the invisible data highways that let your devices actually function and the surprisingly clever traffic rules that prevent total, catastrophic gridlock. Let's dive in. Seriously, just think about it for a second. Inside one single tiny chip, you've got the main processor, the CPU, the graphics unit, memory, all sorts of sensors, timers, dozens of different parts all trying to talk to each other, all at the same time. It's an incredibly complex, bustling city. And without some kind of traffic management, it would just be complete and utter chaos. So how on earth does it all work so smoothly?
Well, the answer comes down to something called AMBA, which stands for the Advanced Microcontroller Bus Architecture. It was developed by ARM, and you can think of it as the master rulebook for all the roads inside our little chip city. And today we're going to focus on two of the most critical road types in that city. The quiet local streets, known as APB, and the massive high-speed superhighways, called AXI.
Okay, first up, let's take a little drive down the local roads. This is the Advanced Peripheral Bus, or APB for short. And you need to know, this road is not built for speed. Not at all. It's built for efficiency and rock-solid reliability on the quieter side streets of the chip. So APB's whole job is to connect all the low-bandwidth components. We're talking about the parts that don't need to send huge waterfalls of data, right? Things like the settings registers that just tell another component how to behave, or a simple timer that's just keeping count. It's all about doing the simple jobs really, really well, without wasting a drop of energy. You see, APB's entire design philosophy is just keep it simple. It's incredibly low power, which is absolutely crucial for battery life in your devices. It's non-pipelined, which is a fancy way of saying it handles one task at a time, making it way simpler for engineers to design and test. And with minimal signal overhead, it doesn't need a lot of complicated wiring. It's just the perfect, no-frills solution for all these everyday tasks. And you can really see that beautiful simplicity in how it moves data. An APB transfer is just a straightforward two-step process. First, you've got the setup phase. This is where the master, let's say it's the CPU, decides who it wants to talk to and gets the address ready. Then you've got the access phase, where it gives the green light and boom, the data transfer happens. That's it. Simple as that. The source material for this gave us a fantastic analogy that just makes it all click. Think of it like a city bus stop. PADR, the address signal, is your final destination. PSEL, the select signal, is the specific bus stop you want to get off at, the exact peripheral. And PEnable is the signal that confirms the bus is actually moving and your trip is happening. And this simplicity is right there in the signals themselves. You only need this handful of signals to manage the entire conversation. PSEL to choose a device, PEnable to kick off the transfer, PReady for the device to say, yep, I'm ready, and PSLVER in case something goes wrong. It's just a really clean, efficient system. Okay, time to leave those quiet local roads and merge onto the superhighway. Buckle up because this is AXI, the Advanced Extensible Interface. And literally everything about it is designed for one thing and one thing only: raw performance. AXI is the absolute backbone connecting the power players of our chip city. We're talking your main CPU, your graphics processor, the high-speed memory controller, all the heavy hitters. They all need to move massive amounts of data as fast as humanly possible. And that is AXI's entire reason for being. And the source of all that power is shown right here. You see, unlike APB's single country lane, AXI uses 5 independent channels all running in parallel. This means it can be sending an address, receiving read data, sending write data, and getting responses all at the same time. It's a true multi-lane superhighway for data. And AXI builds on that parallel structure with some amazing features designed purely for speed. Of course, the separate channels give you massive throughput, but the real killer feature is something called burst transactions. Instead of sending one piece of data at a time, AXI can request a whole block, up to 256 pieces, in one single go. It's like sending an entire convoy of semi-trucks down the highway instead of just one little car. So, with all this data flying around at these insane speeds, how do you prevent collisions? Well, AXI uses this really clever two-way handshake. The sender raises a flag called valid, which basically says, hey, I have data for you. The receiver then raises its own flag, ready, replying, awesome, I'm ready to take it. A transfer only happens when both of those flags are up. It's a simple, elegant rule that keeps everything perfectly synchronized. And this diagram from our source material shows it perfectly. You can see it right there. The transfer, that moment the data actually moves, only happens on the clock cycle where both the valid line and the ready line are high. This makes sure that no data is ever sent before the receiver is ready for it, and no data is ever missed. It is the fundamental heartbeat of the ASI highway. So we have our simple, steady local road APB and our high-performance superhighway AXI. It feels like a showdown, right? It's time to put them side by side and really understand when and why you choose one over the other. I mean, that's the natural question to ask, isn't it? If ACI is so incredibly powerful and fast, why not just use it for everything? Well, as you can probably guess, it's not quite that simple. This table really lays out the core trade-off perfectly. I mean, on pure performance, AXI is the undisputed champion, no contest. But that speed comes at a pretty steep cost, which you can see in the next two rows, power and complexity. APB is low power and simple. AXI drinks power and is way more complex to implement. And this really gets to the heart of it. You have to choose the right road for the job. Yeah, all that power ACI has doesn't come for free. That complexity means more design time, more verification, more chances for bugs to creep in. And the higher power consumption, that's a huge deal in any device that runs on a battery. Honestly, using ACI to connect a simple timer would be like building an 8-lane superhighway just to connect a single driveway to the street. It is complete and total overkill. And this brings us to the most important takeaway of this whole thing. It's not about APB versus AXI. It was never really a showdown. The real magic, the secret sauce, is how they work together. This is the key. A well-designed city doesn't just have highways, right? It needs highways and main roads and quiet little residential streets. Each one serves a vital and totally distinct purpose. The exact same thing is true inside a chip. So this is how it all comes together in the real world. A typical modern system on chip is a hybrid. It uses that AXI superhighway as a high-speed backbone for the big stuff, the CPU, the GPU, the memory. And then there's a bridge that connects that highway to a slower, much more power-efficient APB network for all the other little peripherals. You literally get the best of both worlds, insane performance exactly where you need it, and low-power simplicity everywhere else. So as we wrap this up, here's a final thought for you. We are constantly pushing our devices for more performance, better AI, longer battery life, all in smaller and smaller packages. And that puts an incredible amount of pressure on these internal data highways. The real question for the future is, what comes next? How will these protocols, these rules of the road, have to evolve to handle the unimaginable data traffic of tomorrow's chip cities?